Hello again.
There.
Hello.
Hello, guys.
Oh,
Hello. Okay, almost everybody here. Let's wait a couple more minutes. So let me share just. Okay, here's Mark, and I think then we're full now. So let me just share quickly with you the location of the repository that holds all the materials. So that's, I'll put that into your link, into your chat, or that chat. Okay, so if you want to take a note of anything at all, that would be this URL. I think you should write that down, or whatever. Maybe I should put a link on this website somewhere. So that URL is going to take you to here. This thing is what builds the website that shows your compiled notebooks. Okay, so but why is this interesting? Well, because here, other than the source code for those notebooks, you also have some explanation and some notes. Okay, so I wrote some stuff here that I may not be able to say out loud, and so so there's a bunch of things that may be interesting to you. For example, some homeworks. If anybody wants to do more exercise, here are some homeworks. This is kind of the plan of what I prepared anyway. I don't think we're going to make it through everything, but fine. Got to be ambitious, right? So it's all there, and so that's it. Okay, so for everybody who's late, I just posted into our Slack, into our chat, this URL, which is the URL of the repository that has all the materials in it. Okay, so let me just put this again for the ones who were late. I'm not sure if they can see it. Okay, so here it's again. I would just take a note of this website, and then you can always go back there. Okay. In particular, just briefly, if you want to do more exercise and want to know more about all of this, you click on one of those. Let's go there, for example. It will open this, so this is the homework, and you can download here you have to do those in Pluto notebooks, but it's easy to do. But more importantly, this is part of a larger course that I usually run. So here you have a bunch of material, a bunch of lectures, different stuff that may be interesting. Okay, and they're all sort of self-contained, so they're all run in the same way. There's always a notebook. You can always grab the notebook and just go through it, run all the cells, and hopefully understand more. So if there's more demand for stuff that we won't have time to cover, then go to that website and have a look around. Okay, again, you can go to there from this section, homeworks, which are the homeworks of that course.
Florian, we didn't discuss this thing of the notebook. No? Are we supposed to have the Pluto thing? I mean, is it something we have to download, or how does it work?
Yes, so no, we didn't discuss it, but now is a good time. So yes, by all means, I would install the package. You've seen how it works to install a package. It's very easy. You just type this one and you say add Pluto. It's easy as that. And then you do what I did. You look, that's what I did. You say using Pluto, and then you say Pluto run, and that's it. And then it will open your browser at this URL, and then you can start hacking away with Pluto. The
How do
plan
you
is that
download it?
later on, say it again.
Sorry, how are we supposed to download it? I don't remember.
So installing a package is very simple. You start Julia and you do the square bracket closing like this. You go into the package mode and you would say add Pluto. Okay, so that was the thing we did with the distributions package. Remember, we said add distributions instead of Pluto. Okay, and so that's how you add the Pluto package. And then after you've done that, you would, it's a good practice to then say status and see whether you have it installed. So if I do that, you see I have indeed the Pluto package installed in this global environment next to the distributions that we used before. By the way, now suppose I don't want to keep distributions in this environment. I can simply do remove distributions and it will kick it out. You see all of the red stuff will be gone. And I can again do status or just st for status. And you see I'm only left with Pluto. Okay. So you can manage these environments like that.
Sorry, instead of Pluto, can we work in Jupyter as well? Or
of course, you can work in Jupyter as well. Great question. So the Pluto notebook, this one here, or rather this one, is just one notebook environment that you have. Okay, you also have the very well-known Jupyter environment. The package there is called iJulia. And so if you go to ijulia.jl, you will see this package. Okay, so it's this one, and it works very well. Okay, so there's no problem. You would add it in the same way. You would say add iJulia. iJulia, hit enter. It's going to install it. And then you can say using iJulia, and you have the function notebook, which is going to open a Jupyter browser. Okay, so definitely that is also something that works. Okay, good. But I mean, for now, this is not very important for us. Okay, these are all things that you can do with the core language. Now we just want to know more about the elements of that language. But you know, these are good questions, so keep them coming. So before lunch, we stopped right here at this line, which did something kind of magic. So there's a bunch of stuff going on in here. So let's go slowly. But basically, the output of that whole thing was an array. Okay, so something with several elements. And those are called collections. So let's look at collections now. So in Julia, we have got different types of what is called collections. And we call collection everything that you can iterate over. And those things are called iterables, okay, because you can iterate over them. I'll just do this. Iterables, because you can iterate over them. What does iterate mean? Well, it means you traverse them in a certain order. And you can do stuff with each of the elements. You look at them. Sometimes you can only read them. Sometimes you can write them. Okay, that depends on the type of collection. The indexing, or usually what you think of as getting an element from a collection, we do with this operator, with the square bracket operator. Okay, so for example, if C is one of those collections, this expression C square bracket 4 would get you the fourth element of C. Okay, note the difference to MATLAB where this is a round bracket. Okay, very good. The one thing that's noteworthy, not for you guys because you are MATLAB guys, but if one of you is a Python guy, notice that Julia indexing starts at 1 and not at 0. Okay, just so you don't make any bad mistakes. Okay, so let's look at a couple of collections, iterables. First thing we look at is tuples and named tuples. All right, we encountered those before. Someone asked me, what is the thing with the bracket? So that thing right there. So I've got something that I'll call W, and so I make the round brackets, which is going to create a tuple. It's going to have 1, 2, a string, and a pizza slice in it. Okay, just again to make the point that this can be anything. It's just a symbol. Okay, if I open it like this, it's going to tell me the first element is 1, second is 2, third is this string, The fourth element is the number 5. And then I can index them. So with the square bracket, I get the first one out. That was number 1. With the third, I get the third one out. That's what's up. And that's it. So there are short sequences of values that you group together with this round bracket. Okay, it's not an array because those things are immutable. Immutable means you can't change them once they're created. Okay, so if I try to do this, I say, I want to give the value 10 to the fourth element of the tuple. It says, no, you can't. There is no method set index. Set index means you want to set a value at a certain index. Okay, you can't do that. Tuples are immutable. That's why we use them only for very short things, you know, to give back from a function more than one value. For example, we group these things together, or for keyword arguments, etc. So these are not things that you would use for array operations, you know, where you have many values together. So those are tuples. There's also named tuples, so you can have the same thing, but you give a name. Like here, WW now is much the same, but each element gets a name, right? So I can just call them 1, 2, 3, and the last one I call burger, just because, again, these names can be anything. Okay, so I index by position, I get the first one. I can index by name, and I have to use this thing, the colon, and the word is called a symbol. Okay, so colon 3 is the symbol 3. It's a kind of special string. And I can also use the symbol of the burger, and will get me this element, which is the number 5. Or the third thing, you can grab stuff out of this with the object assessor with the dot. Okay, so you ww dot and the name gives you back the element that's called 2, which is this one. Okay, so these are very handy if you do, you know, for example, return values from functions or inside functions and so on. So they're kind of very nice things. Next up are ranges. So they're very useful, of course, to index, for example, arrays. So you know what the range is. In MATLAB, you call those linspace, I think. But basically what it is, it's a sequence with a fixed step size. So from one to the next element, you have a fixed step size. The key thing that you should know about Julia ranges is that they're computed lazily. So differently to other languages, you don't have to store the entire range of values. So if you create 1 to 10 in R, you create a vector that has 10 slots and 10 numbers in it. In each slot, there's a number. Same in MATLAB. In Julia, you don't have to do that. Instead, it just stores 3 numbers: start, stop, and step. Okay, and in this way, you can create huge ranges, which will be very memory intensive, by just 3 numbers. And then at the moment when you want to grab a value from that range, it's going to compute it on the fly. Say, okay, I want the, well, at some point I'm going to index that, but basically, let me just quickly show you. So here you create a range with the usual colon operator. So 0, steps of 2 to 12 gives this range object here. The type of this is a step range of int, which means the start and the stop. The start and the step are ints. There's another way to create it like this with the usual range command. So there's different methods. You can look those up in the help. And depending on what the number size is, they have different contents, you know. So they look slightly different if they're off the grid, let's say. And I guess somewhere I'm going to use them. So yeah, you can collect them. So you can create a data array of it. If you say collect on the range, then it's going to create an actual vector. So that's what you do in R. You do this. If you want that, you can collect the whole thing and you get an actual vector. But if you want to just have the 5th element of this range, it just computes it on the fly. Okay, and again, you cannot set values. You cannot change the range. The range is what it is. It's immutable. Okay, so this is an error. I cannot set index 5 to 2. Okay, you can do ranges on any sorts of stuff. anything that's iterable. So here's just something letters. You can do a range of letters starting from A to Z. Just do this. Okay, so that's what that is. So then if I do letters 10, it's going to give me back the 10th letter. All right, that's J. The 4th letter is D, and so on. You can do colors, so you can do a range of colors, which is kind of nice to make plots when you want some sort of gradient. So there's red. Colorant keyword is from the colors package that I loaded in the beginning. So you can represent a color here. And that's just the usual range function. So that's the same range function, but we've seen that before. It's specialized in this case for the input arguments color. Okay, so if I give it a color, the range function, it knows what to do. It's not going to yell at me and say, what do you want with this color stuff from me? It knows that, you know, there's this way that you can build ranges out of colors. Because the person who wrote the colors package exported a function called range that we can use now. Okay, so that's how this stuff works. We'll talk about that later. Same idea with dates. Of course, that's very useful. We create ranges of dates sometimes. So here's from the dates package, which also I loaded in the beginning of this notebook. Here's I created a date. So that's going to be 29th of January 2014. And I make steps of 1 day up to this other date. And then I can say, whatever, what's the second day of that range? Okay, so the dates package is actually really nice. So look it up if you want. You can do durations, and it's very sophisticated. I think it's great. It's at least as good as the R package. What's it called? Lubridate, which I kind of like. Anyway, so that's there. I'll leave that for you to look at. Okay, next thing we'll look at is dictionaries. Very useful. I love dictionaries. They're very versatile and great to store information. They're similar, if you know a little bit of R, they're lists in R or similar to R. They're the same thing as dicts in Python. And you can create stuff like that in Fortran if you're very good. And you can have you can have a map in C++. But anyway, so what it is, it's a key value pair. That's what a dict is. So you would have a key, and associated to that key, there's a value. So for example, think of a phone book, right? So if I write phone book is dict, the key is John. There's this arrow, that's the value. And Mary, I've got two basically elements. If I open this, I've got, you know, the length of this is 2. There's Mary and there's John. And each of those has associated with it this number, which could be their phone number, right? And then I can, sure.
Just a curiosity. Can you put instead of a number vector in these dictionaries? Or
yes, okay. Very good, excellent question. So short answer, yes, you can put there whatever you want. Okay, that's why they're so versatile. You're not restricted in any way. You can put whatever you want, and that's how I use them most of the times. If I need to collect, let's say, results from some experiment, you know. One result may be a plot. So one of these arrows goes to a plot. One may be a table. One may be a whole data set. And one may be a function. Okay, so yes, that's why they're great. They're very versatile, exactly like R lists. Okay, in an R list you can put whatever you want. Of course, there will be implications for performance then. You know, so in this case, they are all of the same type. The key is a symbol, and the value is an int. Okay, so they're all of the same unique data type. If you make this more diverse, you won't be able to specialize this to int values. So if the value once is a plot, once is a table, and so on, that won't work. But most of the times I don't care about that. Most of the times I just use this to carry around stuff. After I'm done with the big computation, I just collect it here and I take it with me to just keep it all nice and tidy. Okay, so then how do you use it? Well, you use the key. So if you know the key, you know John, and again, notice that I use this symbol thing here. So colon and some word, I get the phone number of John back. Okay, and you can't index it by position. Okay, so in our list, you can index by position and name. Here you can only index by key, whatever that is. Notice that the key, of course, could also be a number. Okay, so that's fine. Look what I do here. I say phone book 1 because I wanted the first index, but that doesn't work because there's no key 1 in this dict. There's only symbols. Okay, so then what can I do? I can add a new, so once the dict is created, I can add a new key value pair with this, just with the assignment operator. So now I'm going to add Peter. I'm going to give him his phone number. I have to be consistent. Once the dict is created, I cannot change key halfway through. So now I want to add Florian as a string. It says, no, that does work. Okay, so there's an error. You cannot do that. Wrong type of key. Okay, so once it's created, you have to be consistent with these things. So the key has always to be the same data type. Then in the value, you can have all sorts of stuff, but the key has to be consistent.
But it can be a string, right?
It can be a string.
Yeah,
it can be anything. Can be anything. So I think we do that here. So see. So here's what do we do here? We have a dict constructor. So this function dict, and you can give it arguments. It will create a dict for you. So see what that does. So so we say k is going to be the key. It's going to be associated to whatever's right of the arrow. In this case, wow, what is this? So rand is the function rand, which draws random numbers from something. It's going to draw it from the array true and false. It's going to randomly choose between true and false. And it's going to choose it for 1, 2, 3, or 4 values randomly chosen. Okay, so just to make the case that you can have differently long elements in there as well. And I'm going to do the whole thing for k. So you see that k here, k shows up here and there. And you can see that I say k, and in the end I say 4k something. So the thing is going to do the whole thing twice. Once when k is 1, and once when k is 2. Okay? And so this is a very nice way to construct these dicts in a very handy fashion. Okay, so you can just write it like this, as if it were a loop, or in your head you would have some sort of summation sign maybe, and an index and so on. So I find that very nice. And then let's just look at it. So k1 is here. That must have chosen here 3. And then it's sampled 3 times from this thing. So we had false, true, false. The other one, number 2, which comes here first, had to choose here 4 by chance, and so sampled true, true, false, false. Okay? So sorry if this example is a bit contrived, but I just wanted to, as the question was before, those can be totally different. Okay, those elements. Also notice that they're not ordered. You see? 2 comes first and then comes 1, because it's totally irrelevant, the ordering here. You only go by key name. So the technical term of this is a hash list. So there's no ordering. You just have a phone book, as it were, and you have to look up the key and then the value. If I'm already talking about that, there are ordered lists. Okay, so there's something called the ordered dict, which is part of a package called data structures, which I didn't load here, but that will preserve the ordering. Sometimes you really want to preserve the ordering for some reason, then you can use an ordered dict. Ordered dict, let me just put that as a comment here maybe. Ordered dict preserves ordering data structures. Okay, great. Okay, then so there's a couple of more things with dict. So you can call the function keys on that thing, and it will give you back the keys in the dict. And values does the same thing. So it gives you back what are the values. So you can think of it left of the arrow, right of the arrow, in case you want to look at those. If you want to use them, you can call the function collect on them. I did not do that. So because this is just an iterator, so it's not the actual vector of values. If you want that, you have to do collect values phone book. Then you will actually get a vector of values out. See, there's a slight difference between a value iterator and the actual values. These ones you can't use. This is just something that iterates over that dict. It's not the actual values. Get them like this. Maybe I should leave this here. It's not so irrelevant. Okay. Right, so what can we do otherwise with this dict stuff? We can iterate over it, of course. We said it's an iterable, so we have to be able to iterate over it. How does iteration work in Julia? Very simple. You have how come I didn't show you that before? Ah, that comes later. Okay, that's poor planning, I guess. So how does iteration work? Well, like this, you say for and something you iterate over in some iterable, do something, and. Okay, so now please don't get confused with that stuff here where it says with terminal do and. That's only for me because in Pluto you can't print to the console. So I have to do that stuff that it will simulate the console up there. So don't worry about this at all. Okay, so for you, forget about this and the first line and the last line. So basically, but this is kind of nice. Look at this. So you iterate over the phone book thing, which is a dict. You see, I'm giving two iterables, two iterators, a K and a V. Okay, and so this is very cool because he knows that the first thing I want to iterate over is the key, and the second thing is the value, and I can do stuff like that. Then I can say the number of K. So I'm going to I just interpolate the key into that is V, and then I just print it to screen just to see what that is. But you can see that this is nice because you can actually work with this. So you will have your structure, your dict of model outputs of plots. Where the key is the name of the plot of the experiment and the value is the plot. While you can, for example, loop over that, grab the name and save the plot to a file with that particular name or I don't know what. Okay, so this is very useful.
Florian, just a quick question again. In here, if the value were vector, for example, do we need to use the collect in the loop or that wouldn't be necessary?
Well, so in this example, no, it wouldn't be necessary. You would just print it. So it would. Your question is whether the print function would know how to show that stuff.
No, it's not about the function. It's about the for loop. If I want to use, for example, a vector associated to the key K within a loop, I don't need to collect that.
No, you don't need to. Okay. No. You no. So I mean, let's just try this. So you just tell me whether that's what you wanted. So here's a dict. And there's a first key. I'll just call it first. No, I'll just call that 1, and that's a number. And then there's a 2, and that's 2 numbers, 2 random numbers. And so what does it look like? It looks like this. Okay, so 2 is a vector. This other one. You see it switched to any now. Okay, so the key type, the value type of this is any. It's no longer a unique type. It has to accommodate many different types. That's why I called it any. And so so you want me to, I can print this again if you want, like this. So I'll call this E0. See what it does. So it just prints the array for me. Okay, so in this case it works.
Perfect.
Okay? So it wouldn't, for example, it wouldn't know how to print here a plot. Because you can sometimes make sense to print the plot to the console, okay? But no, otherwise that works. So you're free to use those in very flexible ways. Final thing, you can get for each element, each element has a first and a second associated. So instead of key value, you can call that first or second. That's what they want to call it first before. So you see, you can use the function filter, for example, to get all the Peters out of your phone book. Okay, phone book is a dict. This thing here is an anonymous function. Okay, so when in MATLAB you do something like this, I don't actually know how you do in MATLAB, so I don't know, but I thought there was some add involved. So in Julia, an anonymous function works with the arrow. Okay, so that would be the anonymous function that squares x. Okay, so that's just a notation. So here I give an anonymous function to phone book, and I use it in the filter function. So the filter function is going to apply this function to the phone book dict and check where this is true, and wherever it's true, it's going to keep it. Okay, so it's going to keep the values where this condition is true. And what's the condition? Well, the condition is if the first thing of each element, which is the key, is equal to Peter, you return true. Okay, so he's going to keep those. And here, if I do this, you see the only thing that's left is Peter, because only he was called Peter. And similarly, if I want to search for values, I can do second. So I want to have all those with a phone number that's greater than 12,500. And so it turns out that's those two, Peter and John. Okay, so you can filter on keys and on values in this kind of way by using first and second in the filter function. Okay, great. Time for a little exercise. So that's again on your website. So if you go to the last, I think it's the final, it's the end of this lecture. You go there. That's your little thing, your little exercise. Let's see if we can do that. I'll open breakout rooms and okay. Go open all rooms. See you in a bit. Okay, everybody's back. So who was successful? I know the time was short, but anyone?
Not me.
The last step
Yeah.
was kind of a bit tricky.
Yes, yeah, exactly. I thought so, but that's great. Everything
Oh, we
was-
forgot to filter.
you were cheating. Okay. So, so here's the solution. So create this dict as we did it before. So we'll use the constructor dict. Just say k is the key. The value is k to the 3 and k in this. You see, this is this range object that we should have created. The alternative, of course, is to write out the values. Just say k is in this vector 1, 3, 5, 7. We haven't talked about vectors yet, so that's why I didn't tell you to do that. And then finally, you filter on this. So I said, get all those that have a value greater than 21. You could do it like this. You call the filter function on the dict, where the function to filter by is this one. Okay. So that.
Question: if I were to specify the k in terms of a range from the beginning, 1 to 7 with 2, and then define another variable, let's call it k to a square, and make a power of that. I see that it becomes a vector.
Yes.
And then filtering, giving exactly this comment with filter doesn't work. Why? So suppose I write k is equal to 1, double dot 2, double dot 7.
Yes.
Then I say k3 is equal to k dot power 3. K dot power 3. And I
Why is this weird?
dict k implies k3.
So you
So
want
this
to.
is a vector. This is not
This
a
is a
range anymore.
This is
So
a vector. Yes. This is a vector.
the definition of k.
Your connection is really bad. Maybe
They are different, no?
try to turn off your video. Maybe it's gonna work better.
So now create a dict and then filter it. So sorry about this.
No, so when you
there has
wanted
been
to create, you
technical
wanted to create a dict out of k and k3.
Yes.
Like the values are there.
Exactly.
Yes. So that you can do in the following way. You can use the function zip. So what is zip? Zip is going to run multiple iterators at the same time until any of them are exhausted. Okay. Well, you can. So let's look at an example. A is 1 to 5. B is this, same length. You can zip this together, and we will get something that combines them. So let's see if that actually works. What I just said. So I want to run zip on k and k3. Okay, indeed. So it creates this dictionary that's going to have these things. Okay, and so then at that point you can filter on it, as we did before. Okay, so you would have x second greater than 21 on that dict, and that's going to give you those things. Okay, so I guess your question was just how, if I have two existing vectors, how can I combine them into a dict? That was achieved with the zip function, with this construct here. Okay, I'll just add this here. Question: existing vectors into dict. Let's just do it like this. Okay, great. Good. Let's move on. So that was that.
One question, Florian.
Sure.
When you do this p second in this example, what are you doing in this range?
Well, so yeah, so the whole thing, everything that's stored inside the dict. So let's just see, where's my dict. I'll just create this one here. So D, what is the type of D? Okay, it says it's the dict. So what's going on is that internally those things are stored as pairs. So each element is a pair. It has two a pair has two things, right? It has a first and a second. So you can see also dict. So you see a pair is just this. So a pair is this thing that we write X arrow, double arrow to Y, that is represented as a pair. And so this pair thing just has two elements, a first and a second. So if I create my pair is going to be key X should be equal to 3. So the type of P is a pair, and I can get two things out of this. I can, first of all, let's see what are the field names of type of PP. Okay, there's two field names of this type, first and second. And so that means we'll talk about that later, so don't worry. So this is a data type that's composed of other things. So I can just get with the object accessor, with the dot, I can just get the first out of this, which in this case is the key, and the second. Okay, so those are the fixed names of a pair. It has a first and a second. Now in our example, D is dict, so the first of each line is the key, and the second is the value. And so that's why I can filter on this. I can filter on the second because I want to check on the value, which is the right-hand side here. If I filter on first, I filter on the key. Okay, so in this way I can pick out elements from the dict that I want. Does that answer your question?
Yes, thanks.
Okay, great. Good. What's next? Let's see. Let's go to the next notebook. Basically, for you, there will be here two functions. I'll start this up so I can actually use it live. So two functions. So you see this is nice to look at for you. You can look the stuff, but of course it's not live, so you can't run. So there's no server behind it. It's a static page, but it's enough for you to look at the questions, which is the scope of this whole thing. To remind you maybe later on what we did. Of course, you will be able to run those notebooks, so that doesn't mean they don't run, but you have to copy them to your computer and run them. They won't run in your browser on the web. Okay, good. So next thing, programming constructs. What do we think that could mean? We think iteration loops and functions. We already started with this, but let's just go a little bit deeper here. Okay, so we have already seen how to assign variables. That was easy. We use the equal sign. Y is equal to 5. We can have more than one assignment in a block. So we use the begin end block. We can do many assignments at once. That could be useful. So you say y2 is all of that. So y2 is, so you see, so what is this doing? This is like a little function. You see, you assign 3 to B, 2 to A, and you do some computation. And so the last thing will be assigned to y2. So y2 is 3 times 2 minus 12 is minus 6. But you created those variables along the way, so they show up here. So B is 3. Okay, y2 is minus 6, as we said. Okay, so just to point this out, you can do stuff in these blocks, which they just group things together, begin end. Okay. Loops, we already had that. Should have done that before, but here's how a loop works. Very simple. You've got the iter variable, which is just some index, or we've seen before, can be tuples of indices, 2 or 3, doesn't matter. Just go over those, over an iterable, and then there's the loop body. So what do you do with the iter variable? For example, you could run a function g of that thing or whatever. And the key thing is that iter variable only exists inside the loop. There's a local variable. Okay, so if I run this, for example, you run something like this, for I in 1 to 3, print ln I. Okay, so then I do that again. I have to use the with terminal function, just that this prints here, but you see, it does what you expect. It prints 1, 2, 3. Okay. The key thing, of course, I wanted to point out is that if I then call I outside the loop, it doesn't exist. It says I is not defined because I was only in there, you see? So that's something to keep in mind. A loop creates what is called a local scope. Okay, so everything that's defined inside it will disappear once you exit the loop. So of course, if you have something outside the loop, it doesn't disappear. But I hope you didn't.
Florian, how do you write this in? With the LaTeX?
Yes, it's LaTeX, exactly right.
Okay.
In, not in, you know, all the stuff. Okay, so these are actual functions, in and not in, as you see here. Very, very, very handy, by the way, to to search for stuff. So if this is a vector as well, you could look the ones that are in both sets. So this is very cool.
Just a quick question
sure.
about things disappearing within the loop. If you had, for example, a loop and a function, well,
sorry. Yes.
So if you have a loop and you are computing a function within that loop many times, and you want to keep that result, you pre-allocate that variable outside the loop and then substitute it with the value of the function, or?
Yeah, exactly, something like that. So exactly right. So you would kind of create something outside of the loop, for example, an array or a dict, as we just said. For example, an array with as many elements as you want to do looping operations. And then, of course, you can index into each location of that array and just write the result into it. Okay, so that's exactly like that. And so we'll later on see a bunch of approaches where you create this array in one go. Like, so what you just said is totally reasonable. But so we'll get to there. Okay, no problem. Okay, we can iterate over multiple things at once. I think we already seen that. So again, we create a dict with two elements, A and B, and we already did that. So there's no value in doing this. I did exactly that. What I want to show you though is the enumerate function, which I think is very, very nice. So what does it do? It says for some iterator and a second iterator, I call that X and Y for index and value in enumerate of some iterable. So round 3 is an iterable because it's a vector with 3 numbers, right? And so I can give that to enumerate. Enumerate is going to give me back 2 things, an index and a value. And so I can go over those together. And so in each step of the iteration, I have both the index and the corresponding value. And then if I print it, it's going to look like this. Index number 1 has value so and so. Okay, and that's very nice because, I mean, for example, if you do the most stupid value function iteration, you always want to know the value of the index of the state and the corresponding value. And so that's very nice because you have both at once. You don't have to worry whatever which index was that, blah blah blah. Just go with this, and you can work with indices and values together in this way. Okay, good. While loop, of course, is all the basic stuff. So you have a while loop. Okay, while. So what's different? Well, you use a counter from outside. So n equals 0, while n is smaller than 4. Go on and add 1 maybe, and print, and then it's going to stop. Okay, so very basic. Everywhere else, if else are standard. You have to always finish that stuff with end. So all the blocks need to be finished with end in Julia. Condition, else, you can have an else if there, etc. So it is all very basic, I think. One thing that is what I find nice is this ternary notation. So where you can put an if else block into a one-liner. Okay, so see how it works. It says condition. So the first thing is the condition. Condition, question mark, if true. If not, what do you do if it's false? Okay, so how does it work? So here's the condition, m less than 4. I defined m here, it's the number 4. The condition is m less than 4. You have a question mark. What do you do if it's true? Well, you do something here. I print, this is true. Else, do this. Okay, so in this case, it's greater than or equal 4, so I want to print this. It's just it's exactly this, but in one line. And so this is very nice because you can use it, for example, in a function call. You know, you can say, well, if the input argument is this and that, do something, whatever. Of course, that's not first order Julia, because there should be a specific method for whatever input you give it. But anyway, it's very handy to have this in one line sometimes. Okay, functions. Well, here we are finally. Functions are basically the core of how you do work in Julia. So let's look at it. I'll say that over and over again. You should put all of your performance critical stuff into functions. Okay, you must put stuff into functions. Julia is not working like a scripting language like MATLAB or R, because it's just a bunch, run a bunch of stuff in a script. That's not the way it works. Why? Well, because you have the compiler which runs underneath Julia, which needs to analyze your code. And if you don't do that in a function, there's no chance of doing that. Okay, so you will be very poor performance if you put everything into global scope. All right, 2 ways to define a function. One, you have the keyword function, and you give a name like f here. You have round brackets, and you put the arguments that have to go with this function. Of course, could be no arguments at all. Then is the function body. What does the function have to do? Right, you just do what it has to do. Again, is a local scope. So y is not visible outside. It's only visible in here. You exit the function, y disappears. And you return the last value by default. Or if you want to be explicit, you can write return that thing. Okay. Actually, I think that's a typo. It shouldn't be like this. It should be. There's no bracket here. I think. I don't know. Okay, that's the first way. Second way. I
don't understand this. Why do you put the y at the end? What are you doing here?
So here I'm returning y. The last thing, the last value is going to get returned. So if I call f of 1 of 2, that returns 4 because 4 is the last value that is returned. If I change that now, so.
What do you mean the last value? What is the first? Are there other values?
Well, the last operation, the last line. So, for example, you know, I do this and now I do that. You see what I mean? So the output now is 12 because I gave it 2. 2 to the 2 is 4. 4 times 3 is 12. It's not this one. Does that make sense? So if I put 0 here, the function will return 0.
If you don't put anything, you would still get y.
Yes, because that's the last thing that's executed. So if I do this, I still get y because that's the last thing that gets executed. So it's just the last thing, the last operation is returned. Okay. Again, if I do this and then I return -1, the function will return -1, whatever else happens, right? So that's what I meant, and so by default you can just write it like this. That's fine. You don't have to do anything. It's going to return y. Okay. Good. This is the second way in which you can do this. So there's a second function. I call it f2 on one line. You see, function name argument equal what does the function has to do. All right, just very brief and very simple for short functions. That makes life easier. Okay, we execute the function, or what we call the function by typing its name and giving the required arguments and hitting enter. And if there's no arguments, you have to give empty brackets like this. Okay, for example, here, as we did above, I'm calling f. So this evaluates f. And okay, I can whatever. They both work. Okay, so that's very basic, but that's important. Next, keyword arguments. So, and positional arguments. So how can you specify arguments? So first you can have multiple arguments in a function by position. So first x, then y, then z, and then you have to give them in the right order. You can have default values for those positional arguments. For example, here in this example, I specify a default value for the second argument to be 2. And you can have keyword arguments. So after the semicolon here, I give a name, Z, and I give a value 3. And so this is what is called a keyword argument. The function itself does this operation, x times y times z. Okay. There's a quick question here. So I define this function, and you see the Julia prints G. It says generic function with 2 methods. And so my question is the following: why 2 methods? I'm going to tell you what a method is. A method is a specific version of a function.
The default values?
Yes, exactly. So it's not default value, but it's the keyword stuff. So Julia is going to create one version where you give the keyword and one version where you don't give it, and it's going to fill in what you wanted. But yeah, basically you're right. It's the default value. So it's going to be by default 2 methods that get created when you have a keyword involved. Okay. So let's try this out. G1 is 6, he says, and so that's because I put a 1 here in the x. So that's 1 times 2 times 3 is 6. Okay, let's just check this. So yeah, it says true. 1 times 2 times 3 is 6. What if I put 1 and 3? All right, so in the second, the y now becomes a 3 instead of a 2. And so it has to evaluate to this. So that's true as well. And what if I set the keyword z to 0? Well, then it needs to be equal to that. So that's all good, and as it should be. Okay, so that's just how keywords work. Notice that you cannot treat the positional argument y like a keyword. So when you call the function, you cannot say y is equal to 4, because y is not a keyword. Y is one of the positional arguments. It's just the second argument. Okay, so you can't refer to it by name. And you can also not omit the key word, as you were. Okay? You cannot just say G1, 1, 3, 10, because you have to say that the third thing is Z. You have to say 1, 3, Z equal 10.
Is this, would you use this for specifying type of function within the function, or why would you use this?
Why would you use what? What exactly?
The keyword.
You use it in many, I mean, it's just handy, you know. So it makes the function very readable. So if I show you my code and there's a function that says, I don't know, plot x, y, and the keyword is color equal red, you immediately understand that what this function is doing, it's giving a red color to the plot. Okay, so it's just a way to make the code more understandable, and they're very, very widely used in Julia. So you will see those all over the place, particularly, as I just said, in plotting, because it makes sense to have a kind of a. I mean, I guess the short answer is it's very hard to remember 25 positional arguments, right? So, I mean, if you have a function that has a lot of functionality, you won't remember, what was it I should put 4th here, or like, you know. So I guess that's a much better answer.
MATLAB has this kind of thing too, no? That we refer.
Yes, absolutely. MATLAB has this, of course. Of course, you have, at least I think so. I mean, you have these var args, which can be keywords, but I have to say my MATLAB is really rusty, so I'm not the right person. Okay, so let's summarize this, and then let's do a little break. So we have positional arguments that have to go in a certain position of the function, like y in this example. We have keyword arguments, which you have to supply with the name if you call them. If you don't call them, they get supplied by their default value. You define them after a semicolon. So if you define the function, say semicolon name equal value, and you can have as many keywords as you want. Okay, as we just said. Good. I think it's good time for a break. Oh wow, this is a great one. Yeah, but let's do a break first. You guys need a break because that's going to be hard. So everybody stand up and maybe get a coffee or something on board, and then And then we'll see how it goes. Okay, 5 minutes. See you later.
See you.
I think this has to do, the naming and the keywords and the positional arguments for sure has to do with the things of the speed, Luis. Because I think he said something like Julia creates basically two functions, one for the keywords and another one without. So I'm guessing that if Julia doesn't have to parse the extra arguments, it will work faster. So I'm thinking that if you already have a calibration and you have your value function that depends on parameters and you can do them by default or something like that, probably you can get speed gains with this, no?
Yeah, makes sense.
No.
I like because also there's a workspace. Have you seen this in the Visual Code?
I haven't.
The last icon in the left is these three dots.
Yeah. The Julia
see the
repo.
values.
Yes, I have here my dictionary and yes. Okay, I think because it puts there the functions of the packages, I think. Because I have the distributions in here as well. Yeah. I mean, I use a lot the VS Code for LaTeX and MATLAB and everything. I do everything in VS Code, but I wasn't aware.
Yeah, that's the first time I've seen this. I use it for Fortran, and I think
it's great for LaTeX, huh? For example. It's super nice for LaTeX. Oh my God, there are like a million functions in the distribution thing. I'm curious, can you open them?
Also, it's interesting because you can define a function in the middle of the code.
Yeah.
And not anonymously.
Which I think anonymous functions are a waste of time, no? Because if you can do an anonymous function, it's probably not worth doing. I don't know. Oh yeah, and if you can see here, okay, this is super weird because you have, for example, I have the dictionary that we created before, and it has.
And you can see the keys, yeah.
Yeah, but you have also these slots. I have 16 of them, but I don't know what these are.
Yeah, I see it.
Do you have 16 as well?
Yes.
And if you open,
there are 16 keys.
Yeah, no, because if you open the keys, well, no, I don't understand. Because for example, in number 7, I have a very long number. In number 10, I have a very long number as well.
Yeah.
Okay, this I don't understand. But then later you have the keys like 1, 1, 327, 7, 3, 4, 3. Yeah. I don't know, it seems very intuitive to write, no? Very many things are very similar. And it's really cool that you can write the latex like parameters and stuff like that.
Yeah, but it's funny because for example, this in is not a variable that you created and used. Is a like a
it's a symbol that you can use directly there. It's very nice, yeah.
Some cool discussion going on here. Very, very good.
Yeah.
You're already nerding it out.
Yes.
Hold on. Well done. Okay, well, I'm back. The coffee machine is far away, so I had to run around the block. Let's just go there. There'll be time now for you guys to chat. There's going to be a little exercise. Just one thing, we can return more than one values from a function. I mentioned that already before when I created tuples. Okay, so for example, what does this g function do? G takes x and returns 3 numbers, x squared, x3. Okay, so very simple. If I call g2 with the number 2, it gives me back 2, 4, and 8. Okay, so again, very simple to group output together. You want to have a function that returns 3 numbers instead of just 1. Or of course, you can return a dict, as we said before. Why not? Okay, so here's a g function g3 creates a dict when you return it. Okay, and so now you also have the key that tells you that the first whatever this is x squared, x cubed. Okay,
but the methods have to do only with the inputs of the function, no? Or
yes, exactly right. Well spotted. Okay, so we'll talk a lot about this. A method is a particular instance of a function for a certain data type. Okay, and so here it says, you see, it says generic function with one method. Generic in the sense not specific, because we didn't say anything about x, right? We didn't say, I mean, x could be anything at this point. We don't restrict it. And so that's why it says generic. Okay, by the way, some nice editing stuff that I did not show you. You could also define the function g2 like this. You can do an underscore. You see? So that's the function g2 now. It's not defined because I have to define it, but that's very nice, right? So you do again \_2 tab, and now it's defined as a function g2, and you can do it like that. So in code that just looks nice. It just makes your life. There's no reason for you to like look at your code and get a headache. It's hard enough. So all of those things, use them and make stuff more pleasant when you work. Having said that, here's a good one. So look how long this is. It doesn't fit on my screen, but it's a fun exercise. So let's quickly go through it. So you're supposed to, in this exercise, of course, you're supposed to write a function, right? That's what we talked about. So open the website. I hope you can still find this. Do you still have it? The URL here? I'm going to put it again into the chat. Well, it's full of this URL. It's all there anyway. So, and it's 2 functions, and you have to go to the first exercise, basically, where all this stuff. I'll show it to you here. It's bigger. Okay, so let's just quickly go through it such that we're all on board what I mean with these things. So it's about Newton's square root algorithm. Okay, so it's not very well known, but Newton, I mean, he did everything. He also had an algorithm to estimate the square root of a function. Okay, and so the algorithm it looks like this. So suppose you want to compute square root of a, where a is a positive number, and you just don't know what it is, and you don't have a calculator. So you have to estimate it. So you start with some estimate x, also a positive number, any number x, which you think is a reasonable estimate. Okay, and then you update your guess in this simple way. So suppose I guess x. The next guess is on the left-hand side is going to be x plus a divided by x times a half. That gives you your next guess, which is going to be better than your previous guess. And you will iterate on this thing. You will take the next guess, put it here and here, get the next guess, put it here and here, get the next guess, and in the end, you will converge to the true square root of A. Okay, I mean, which is amazing in itself, but let's not talk too much about that. So I want you to do this. Okay, and so here's the steps. You know, you're pros at this right now. So you create a Julia file, you define a function, my square root step, which will do this operation here. So the square root step has to do exactly that for A and X. And then you will try it out on the REPL, etc. The hardest part is going to be that you have to print this table, but I show you how to do that. So that's down here. So I mean, if that doesn't work, don't worry about it. Let's first make sure that we can all compute this stuff. Okay, so I'll put you into rooms again, recreate, and then let's do a little bit more, maybe 5 minutes or maybe even 10, and let's try to work on this. Okay, I'll also join the rooms and go make the round and see how people are progressing. Okay, so see you there. Okay, we're back here again. Well,
Yeah, actually, Florian, I clicked the leave breakout room.
okay, that's fine.
So they're gonna take some seconds to come.
Yeah, that's fine. Don't worry. Well,
How do you handle this 2 arguments of the function?
Return and the pair, no?
yeah, you can return. You just return a tuple.
Yeah, tuple. That's it.
Yeah, then return 2 things.
I see.
It works, Florian.
Okay, great. You see that sometimes there's just stuff that's trailing, you know, a faulty character or something. And then, of course, it says can't evaluate that. Okay, make dict. We did that. What was that called? Square root. There's a bunch of stuff. Okay, so welcome back, everyone. So okay, so most people I think were at least partially successful. So 1 or 2, most of them did get to do that. So that's great. So I think the key for me was that you do this stepwise, that you really do first the simple part, which is the inner thing, and you try that out manually. So I hope you got around to do that, because that really makes clear how the stuff is supposed to work. So the way I wrote this is like this. So here's this inner thing, that's my square root step, and you see this very simple expression, 1/2 times x plus a divided by x. Okay, and that you should just try out. So you would just copy this and put it here, and then my idea was that you do my square root step, and you want to know the square root of 4, and you put 6 here, and you see what comes out. It's this number here, and then just to illustrate that, you grab the number and you put it here instead of 6. You can see what happens. It starts going down, right? You do it again, just for example's purpose. Okay, you see, and if you do that over and over again, you'll end up at 2. So it's important that you understand the algorithm, even if it's so simple. But it's very helpful to see step by step what's going on. Okay, the next part of the exercise was to define a second function, my square root, which is now going to iterate on that function that we just wrote, as long as some distance is small enough. Okay, let's look at this.
Florian,
So,
one quick question. I
sure.
did something wrong, and Julia seems to be computing things forever. Control C in MATLAB is to stop.
Yeah, Control C is going to kill it. So you do Control C down here.
Control C should work.
Yeah, like I do here. Control C is going to kill the evaluation. So you ran an infinite loop.
I guess so. I don't know, but it doesn't seem to work. Control C either. Maybe.
Just hit it a couple of times. Maybe it'll work. Okay, so my square root is, you could write it like this. So again, it takes a, the thing you want to know, and x, your estimate, and some tolerance. Okay, here we define a keyword, as we said before, with the semicolon. We have some notion of distance. I'll just call that delta, give it a big number. Then I'll have a new guess for x. I'll just create that, 0.0, and I have a number of iterations, 0. And then I have this while loop, as we said, with a convergence criterion. So while the distance is greater than tolerance, keep going. If you keep going, add 1 to the iteration count, get my new x by using the function that we wrote, compute the new distance, and update x. Okay? And as soon as this is no longer big enough, so it's smaller than tolerance, it will exit. And at this point, x, or x new, will hold the last time. And I return 2 things. In a tuple, you see, x and iters. So, and that's it. Okay, so I think most people got that far, and that's actually quite amazing already that you were able to do that. Then if you were wanting to print this, following along these suggestions here, so down here it says you want to print this table. So the final part should be a function square root table, which is going to, again, loop over something and print this table for us, here's the code that you should use. I can just quickly explain that if you want. So we say square root table. We want to print. So this is printf, is just formatted printing, and you say this is this percent sign says the width of that field is two strings, 10 strings, 10 strings, 10 strings for these words here. A, my square root iterations. I mean, it doesn't matter, forget about this. And then we just do it for a in 2 to 10. We just evaluate our function. We say the starting guess should be square root a to the power 2, and then we print it. Okay, and that will print the table we just said. If I run the whole file as we used to, so I just say execute file in REPL, that should generate this. And if I then call the function square root table, we should get this table that now we see. Okay, so basically just a very simple exercise to make you use functions and loop over stuff. And,
Florian,
yes.
just one question.
Sure.
The at the beginning of the printf,
Yes.
is it because it's a different type of function or something like that, or?
Yeah, exactly. So the add stuff in Julia, they're called macros. Okay, and so a macro is a certain kind of function that. So I was going to say it's a function that doesn't use brackets, but this one uses brackets. But in general, macros are functions that modify your code. Okay, so they take your code, they do something to the code, and then they evaluate it. It's a bit of a weird thing to explain, but they're used many times in Julia just to make things look nicer. Another very important one is the add time macro, which just measures the time of the expression that comes after. So if I do add time square root table, it's going to measure the time it takes to run square root table, which is this. Okay. And so, let's not get hung up on this, but for now, you just should know that add something is called a macro. For all practical purposes, it's a function. Okay. Okay, good. So that was that. That was very difficult in that short time. So well done, everyone. And go back to the website and look up the solution if you're interested. Well, it's going to be on the repository. So all the solutions are on the repository. You don't have to worry about missing any of those. Okay, now typing. We talked so much about typing. So let's talk a little bit more about it. And let's talk about what we call duck typing. What does that mean? Well, it means that the way Julia works is it's always going to look for the best method for a certain input kind. Best in the sense of most appropriate. So for example, for G above, we didn't specify any input type. Okay, so what happens if I give to my G function? Remember what G was. G, that's G, with the keyword and all of that. Okay, so let me try and give a matrix to that function. All right, A is a matrix with random numbers, 2 by 2, and I'm going to stick that into G, and it works. Okay. What if I do 2 A's? A works also. What if I do 3 A's? It works also. What about a string? Let me stick a string into that. Oh my word. It prints oh my word. Okay, that's funny, right? But it all makes sense because for all the inputs that I gave it, the operation times was defined. Okay, so I can obviously I can multiply floats. I can multiply matrices with each other if they have the right shape, and I know what to do with strings if I give them the multiplicative sign. Okay, we just saw that it puts them together, but I can't do this. I can't do number 2 and the word O because why? What does it say? It says no method matching multiply int with a string. Okay, because there's no function that knows how to multiply an int and a string. And so where does that come up? Well, it comes up here because the function tries to do exactly that. Function tries to do, where is it? It tries to do int times string. And at this point here, this is where the error comes from. Okay. So right, fine. So that's okay. What we've seen here, all the different all the different instances here, so G with a matrix, G with a number, G with a string, there are different methods of our function G. See, we never defined them, but it happens that Julia, when we call it with a string, it does something. You saw what it did. It put together words, which is a very different functionality from multiplying two numbers together, right? You could just see that in the output or matrices or whatever. So even though I only define one function G, I got three different outputs given depending on what I gave to the function. Okay, so that concept is called multiple dispatch. The fact that the function f is going to be specialized for certain inputs. And so that's a core concept of Julia, and you should remember that word, multiple dispatch. The key thing is that you don't have to do much to achieve that. It's not that you have to tell the function how to behave. I mean, sometimes of course, you write your own methods and so on, but you saw that we didn't do anything here. Okay, so the function knew itself how to best behave. So we'll talk a lot about this topic. So don't worry if this doesn't make much sense for now. How do we pass arguments? That's also something that differs across languages. In Julia, you pass arguments to a function by reference, which means that you just give sort of a label to the function. The function can look up what is behind that label, operate on that object, and return. Okay? In particular, if we give what is called a mutable object, we heard that already, an array, for example, is a mutable object, then the function changes the supplied object in the caller, not to supplied object, changes the supplied object in the caller. Okay, so we'll see that later on. Okay, that's good because we can modify objects in place. Okay, we can. So think about a large array, a huge array, millions of numbers, and now you want to do something with this in a function, right? So think about what you could do. You could do two things. One thing, you could grab the array, all the data, 1 million numbers, and copy them to the local scope of the function. So you have a copy operation that takes all of this data, writes it somewhere else, do the work on it, and return the result, which is expensive because you have to do the copying. Or you just leave it where it is, somewhere in your RAM, there's these million numbers, and the function will just look at the memory wherever it is and use that to compute. Okay, so we call that thing in place, and that's how Julia functions work. So they work by reference, not what is called by value. This differs across different languages. For example, let's do something. Let's create a function add to first. Okay, here it is. It takes two things, x and y. What it does, it adds something to the first index of x. Okay, so y is going to be a number, I suppose, and you see what it does here. It returns nothing. So nothing is Julia for nothing. Okay? It just returns nothing. Not zero, not nothing, just nothing. Okay, so if we call that function now, I'm going to create a vector v with the ones function, and the v is going to be a mutable object. I can change the contents now. It's no longer like the tuple, you remember, where you cannot change. Here you can change. That would be not so much fun. And then I call the function add to first v2, which if you look here, what is it going to do? It's going to add the value 2 to the first index. Okay, you call the function and you look again at v, you can see that now it has a 3 in the first index. Okay, and so what we do in order to signal this to the user or to ourselves, most of the times you're the user, so treat the user well, is we put an exclamation mark at the end of the function name. You see, add to first exclamation mark. It has no functionality, but it's just a way to signal that this function will modify the input argument. Okay, so we will work in place on the first argument by convention. Okay, so that's how we do this. You see many of those functions in Julia. Whenever you see an exclamation mark, you will know that it basically most of the times doesn't return anything. So you see, it returns nothing, but modifies the thing that you give it to. Okay, Okay, so that's what we did. Usually it doesn't return anything. And so, as I said, there's many built-in functions like that, and they come in two versions. One version that makes a copy and returns a new object, and one that does the same in place. Okay, so let's look at an example. We create V2 as this array. So we just sort the existing V, and V2 now is a new array. See, I sort V, and I get back 1, 1, 1, 1, 1, 3. The sort function just sorts an array.
One question, Florian.
Sure.
The mutable and this other one, the one that was not.
Yes. Yes.
The difference is the brackets. That one is square brackets, the other is round brackets.
Exactly.
Okay.
In the way you create it, that's the main difference. Exactly.
Okay. Thanks.
Exactly. So we'll have an entire section on arrays. I have an entire notebook, so we'll talk in detail about how to create arrays. But yeah, that's in a nutshell. That's it. Okay, so here we sorted this and we get a new thing, V2, which is a new object. It's the sorted copy of V, so to speak. If you use sort exclamation, it's the same V, just sorted. Okay, so let's check this. We can look whether the object has the same memory address in your computer or not. Okay, so let's look at something. V2 is this guy. It's the copy of V that was sorted. So it's 1, 1, 1, 3, but it's new kind of data. Okay, so if I say V2 equal V, that means is the left-hand side numerically equal to the right? It says true because it has the same values in it. Okay, but if I say is V2 equal, so they call this operation equal, which means it's not only numerically equal, but it is the same object in memory, is false because it's not, right? If you go into your computer and search for V2, it's going to be in a different location than V. Okay, makes sense? Just think about your RAM as a sort of a chessboard. In some portion of that chessboard, there's V2, 4 numbers called V2. In another portion of your chessboard, there's V. Okay, same data, same values, but not same data. Okay, it occupies twice the data if you do it like this. Okay, that's very important. So this kind of stuff you should take it to heart. We'll talk about that later when we talk about performance, of course, because that's first order. We want to avoid too much memory usage. Okay, that's it. All right, fine. Questions on that? Yeah.
How do I copy a variable?
Yes,
So
very good
I want to
question.
store more memory.
Exactly. So, well, what would you look for? If you were to search, so here, let me bring up the help here. Copy of X. Whoa, it's behind my head. It says create a shallow copy of X. Okay, so you can copy the outer structure is copied, but not all internal values. You can't read this. For example, copying an array produces a new array with identically same elements as the original. Okay, so there's the copy function, which you can use to copy an array. So copy of V, V3, oops, V3. Let's get rid of this. Right, so that's this. Again, I can do is V3 really equal to V? It's going to say no, because it's a new version of this somewhere else. But that's basically it. You will see that later on. Also, the simple assignment operator makes a copy. So we'll talk in detail about this. Okay, it's a good question. Simple variables, you can just assign them to new names. So if do we have a y here? Yeah, y is 5. Y2 is y. So that's just gonna okay, y3. Okay, y3 is 5. That's going to be a copy. Now it's a bit weird. Yeah, so Pluto is not the best environment to do that because it's all updating at the moment when I change something, so it's going to get a mess. But in general, you can just do an equal to the new name. Okay. All right. How are you guys doing? You're up for a last one? We still have 20 minutes. Okay, let's do it. So next one would be arrays. That's kind of very, very important. So let's look at that. I'll bring up my array notebook, save that, go to the Pluto menu, and bring up the arrays. What's it called? Where am I? Yes, arrays. That's better. All right, go there. Close this, close that. Okay, arrays. Good. Well, arrays are obviously very important. So that's why we'll talk a lot about it. But first, what is an array? Well, array is a container for identical data types. Okay, we've seen lists, we've seen tuples, all sorts of stuff. They could hold different stuff. You remember the dict could be a number, a name, a plot, whatever, a function. Not an array. Array has to have a unique data type. Different from a spreadsheet as well, or a data frame where you can have different types. Okay, so of course you guys know what an array is. It's just they always look like that. The official documentation is extremely good. So go there to read more about arrays in Julia. So I'll leave that here with you and go and check it out. How do we create arrays? Monse already mentioned that. How do you do that? With the square bracket operator, right? So if you do 2 square brackets and you put some values in it, it's going to create an array. Okay, so 1, 2, 3, it's going to make the array 1, 2, 3. Look that by default, everything that is an array in Julia is a one-dimensional column vector. Okay, so be careful about that. That can be kind of confusing, even if I put a comma there. Okay, so those go all into a new line. What's the type of this thing? So type of A is a vector of float 64. Okay, so it tells you it's a vector in the sense that it has many things in it, and it tells you what type does it have in it. In this case, float 64, because these are floats. If you have B, I created B like 1, 2, 3. That you can see is different. It's type int, vector of type int. Okay. Size, you get these with size, and mdims, length returns the total length of the elements. Okay, pretty basic. So the size of A is 3. Notice this is a tuple. This is a tuple with only one element, size. Okay, that's what I say here. All right, we just said what tuples are. You know that by now. These are tuples. Fine. That's repetition. Name tuples. All right, I'm repeating myself here. Forget about that. Creating arrays. All right, let's see what we do here. So we have on this line, I do 3 things in one line. You see, this is kind of cool. On the right-hand side, I have a tuple that has 3 elements in it. This vector, that matrix, and this other vector. And I can deconstruct it on the left-hand side immediately. Okay, on the left-hand side, I immediately destroy the tuple and I assign it to 3 variables. Okay, but you may ask, why on earth would you want to do that? I don't know, but sometimes it's just useful to do stuff on one line. So here I'm creating 3 things. We can just look at those. So the first thing is a normal, well, it's a vector, 1, 3, 6, it's this guy. Second thing is a matrix. See how I did that? I said 1 space 2, semicolon 3 space 4. It's like MATLAB, it's going to create this matrix here. And the last thing is 3 nice words, where notice I did not put a comma and not put a semicolon, which is going to create a row vector. Okay, you can see this is a 1×3 matrix. So Julia has no notion of a row vector. A vector is a one-dimensional array that always is going to be stored column major. Those are going to go down. Okay, there is no row vector in Julia. I'm going to repeat it once more, because you MATLAB guys, you may want that. There's no such thing. Okay, it's just a matrix with 1 row, as it were. Okay, so this is a 1×3 matrix. Okay, we call type of those things. It's just going to tell us what it is. Fine. Okay, string. That's it. Size, number of dimensions. Okay, so again, the numerical vector. This guy has just 1 dimension. So if I call numdims on numvec, it's 1 dimension. If I do the same thing on the string vector, this guy here, the 1×3 matrix, It has 2 dimensions. Okay, again, because it's a row vector 1 by 3. Okay, these are just some little details which are kind of tripping up people. By the way, I should have told you that before. You should go on the Julia website. Let me just, a little detour, a little bit more confusion. You should go to learn, and then it says somewhere, it says notable difference. No, where is this? It's in the documentation. Let me just try and find that. Notable difference. Yeah, noteworthy difference. You see, the manual works really well because it found that I looked for the wrong stuff. So on this page, you have, for example, you're a Power MATLAB user, you can use all of these, look at these things, these little things that are kind of different across the 2 languages. Okay, look, there's a bunch. So I'll just, again, add that to our chat like this, and then you can later on look at this at your own leisure. Okay. All right, so then we have functions ones, obviously that creates bonds of a certain dimension. We can give a data type, so it's going to create zeros, but of data type int, dimension 2 by 4. Okay, so these are ints in there and not floats. You can create falses, trues, and all of the usual stuff. Rand, we already did that. Rand, random numbers between 0 and 1. Random numbers sampling from a certain set. Okay, that can be some numbers or words as we did it before. The fill function is nice. You can fill a certain shape with a certain value. Okay, so this is going to fill a 2 by 5 with 1.3. You can create empty stuff, which sometimes is useful. For example, if you want to pre-allocate a very big array for later usage, you can do it like this. You can say an array of type float64 should hold the value undef, which is Julia speak for not defined. So it's just empty. And it waits for your input of a certain shape. Okay, you can see these are all garbage numbers. There's an NaN floating around. So this is just what happens to be by chance in that particular location in your RAM. Okay, that's just garbage. That's what garbage looks like, in case you didn't know. And then you can use the similar function. For example, similar is going to create the same shape, same data type of a certain input array. But again, watch out, filled with garbage. Okay, so if you remember, RA was this guy, a 3 by 2 matrix of float filled with some random numbers, not garbage. If you call similar on that, it's going to give you back a new array, same shape, same data type, but filled with garbage. Okay. Right, manually creating arrays. We already said that. Square brackets, all right, semicolon tells you next row. All right, how do you do a transpose? With a little tick, and create something that's called an adjoint. And that again, in Julia, uses the same data. You don't make a copy with that. You use the same data of A2. Okay, you don't have to copy all the stuff and rearrange. You just twist around the indexes of the thing. Okay, so that it knows now that you say 1, 2, it means something different than it did before. Okay, vertical cat is putting together vertically values. So 1s and 1.1 is going to create this vector. You have horizontal cat as well, horizontal concatenation. So you have this random 2 by 2 and falses put together. Okay, whatever. You can also look. So here I put together a random matrix of 2 by 2 and the word high in a 2 by 5 shape. Okay. And now you should yell at me and say, but hey, you said they can all only be of the same data type in a matrix. Okay, so yes, that's correct. But see what the data type is of this matrix. It's any. Okay, we'll talk more about that. I already mentioned it. Any is the top of the type graph in Julia. Any is the mother of all the types, I usually say. And so everything is part of any. So any is the highest level of generalization. Okay, so you can do that, but you get very little performance out of this. All right, that's what I just said here. Good. You can also put different length objects into arrays. Okay, so that's funky. So let's look at this. An array is a container, as we know, and no one said that inside a container you can only put stuff of the same length, right? So At least I didn't say so. So you're free to do that. So let's create something called a mix. A mix is an array because I use the square bracket, and into it I'm going to put several things. A random vector with 2, 1, 2, 3, and false and true. Okay, and so let's see what that does. Okay, so it actually seems to work. It creates a vector of float 64, and each of the components is a vector of float 64. So when I say the type of mix, what is it? It's a vector of a vector. Okay, so it's very different to a matrix. You guys know what a matrix is. A matrix is a 2-dimensional array. Well, what that means, of course, each row has the same number of columns, otherwise you can't build a matrix. Here, that's not what you want. Here you have a vector that itself contains vectors. And the key thing is that those vectors can be as long as they want. No one told you that they have to be all size 2 or whatever. Okay, so you can do that. And then, of course, you can iterate over this and grab each vector and do stuff with it. All right, combining existing arrays. So what do we have here? Suppose I want to put together those two vectors, 1s and 0s, 1, 1, 0, 0, and I do it like this with the square bracket. I get something, maybe not intended. I get, again, a vector of vectors, because that's what we just did here, right? So suppose I don't want that. I want 1, 1, 0, 0 in one vector. I have to do this. So I have to have the 1s vector, and I have to do these 3 dots, and then the second argument. And the 3 dots are called splatting. Okay, it means that you take a collection, you unpick it, and you just splat it into the argument slots of a function. So it basically, literally, it does this, right? It does 1, 1, 0, 0 by unpicking all the elements from the 1's function and just giving them one by one to the function square bracket to create this array. Okay, so
that's the same thing as the horizontal concatenation that you showed us.
It's not exactly the same thing. So horizontal concatenation is gonna, so if you do that here, that won't give you the result that you want. If you do hcat 1s 2 and 0s 2, that's gonna do something else. Okay, it's gonna, you see what it does? It just puts next, it would be a column bind in R. It puts like this. If you do, again, if you do vcat, that will work. Okay, so that understands what you want, but doing this thing is not going to do what you want. Well, in that example, okay, what I wanted to do here. That's always a bit confusing, these things, but just trying out a little bit and remembering that stuff. So if you have an existing vector, want to add to a vector and make it just longer, well, you have to destroy the vector somehow and splat it into the function. Okay, we have 6 more minutes, so we can go a little bit further if you want. Yeah, there's a bunch of other things. We won't make it to the next exercise, but that's fine. We'll just continue tomorrow. Okay, there's the push function, which is very nice, which you should know. If you have an array, you can add to that array by just pushing into it. Okay, if you don't know the length of the function when you start computing of the array, then it's useful. So for example, here there's z is an int array, which is empty. So the type of this is a vector of int. The length of z is 0. So the push function would push a value into this, but I cannot push a string into it, of course, because it's an integer array. But I can push integers into it. Okay, for example, I can push 1, 1 into it. First means I push it as the first element. So now z is 1, 1. If I pop z, it pops out the last element. Okay, so I lose one of the ones. Z is 1. And you can achieve the same with append. Okay, append is, well, append depends at the end. Okay, push puts stuff in first. So it's very handy to have this function. All right, last thing is comprehensions, because we mentioned that already. Then my voice will be gone. So comprehensions, we did already one, you remember. So they again use the square bracket operator, square bracket, but inside the square bracket, we now have an expression. So that we call an expression. And you see it's peculiar because it has some indexing as well. All right, so this part is the expression, I plus j. And so this thing with the comma here, notice there's the comma. This will create for us a two-dimensional array. I is going to, so the first thing is going to go into the row dimension. The second thing is going to go into the, so like this, and the second, well, whatever. The second thing is going to go into this dimension. So here, this is going to do I plus j for each of those indices. Okay, and so 1, 1 in the first slot, j, j in the second slot. And so it creates this matrix basically. Okay, 1 plus 1, 1 plus 2, 1 plus 3, and so on. Okay, and it's just going to put them into the right slots, indexed by I and j. And so that's very useful, very powerful, because of course these expressions can be anything.
What would happen if there is no comma there?
Yeah, very good question. Excellent. If there's no comma, it's going to build a one-dimensional array, just going to put them in order down, down, down. Sometimes, if those indices don't form a rectangular thing which you could use to build a matrix, that's indeed what you have to do. Okay, there's an example of this somewhere right here. So suppose the comprehension can also have interdependent indices. So figure that you have this this thing, you want to compute this sum from I to 3, and the second sum depends on I. You see? So this clearly is not a rectangular shape, you see? Because you don't have all the i's for all the j's. I'm not sure if that makes sense, but you cannot write it down as a rectangular thing. So in this case, you just get rid of your comma here. You can compute it anyway, and it's just going to put them one by one, okay? One after the other. I skipped over the exercise, which, why don't you do that right now? Well, as a homework or whenever you want. It's going to be this. You have to compute this budget constraint as a comprehension. That's a one-liner in Julia. So you make an array of this, a very small array, and you just use an expression for this, and you will see it's very simple to do. And tomorrow we look at how that worked, and we continue from there. Does that sound good? Okay. So then I think we should leave it there. If there's any questions, just the best thing is don't write emails, but just write them down somewhere. And tomorrow we talk about them all together. Okay, otherwise I won't have time to manage emails. But you know, think about questions and things that come to your mind when you look at these things. And that's it. So tomorrow at 10 we take it up again. Okay.
Okay, thank you.
Okay. Bye bye.
Bye.
Okay, bye.
Thank you. Bye bye.